Thank you. Today, I'm going to talk about some surprising properties in network protocol and how I'm going to use them to detect and understand adversarial networks. Later, I talk about how to defend against this adversary. So, in summary, this is what I do. I detect network interference. I try to understand the behavior of intermediaries, which does the interference, and try to understand, use my understanding to come up with tools to safeguard users. I'm going to talk about all these three, but before that, let's step back and remember how internet works. In our first networking class, we learned that we have two ends and some intermediaries in between. And the job of the intermediaries is to just route packet from point A to point B. But in reality, internet is very different from ideal view. We have intermediaries that are intelligent. We see intrusion detection system, deep packet inspector, virus scanners. And it turns out, if people who are running these systems decide to be adversarial towards the users, then we have a problem with this infrastructure. I call this problem network interference. Network interference is any action by intermediaries that violates the basic security principle, which is confidentiality, integrity, and availability. One common example of network interference is censorship. That can be several things. For example, blocking. In 2016, we had more than 50 instances where the government decided to shut down internet over their citizens. It also can mean throttling, where the government unique poor performance as a way to discourage users to access the information. Yet another form of that is takedown, where the censor goes to a provider and demands for the information to go down. Google received more than 700 government requests last year. Network interference is not just censorship. It can mean monitoring. In the case of mass surveillance or targeted surveillance. It can mean tampering, where the information between source and destination is being modified. ISPs do that sometimes. Also, it can be used to launch attacks. Great Canyon was an example of where network interference used to launch attacks, and I will cover that in the talk. Overall, we have so many behaviors and so many actors with different conflicting agendas. So the field of network interference is very complex and very rich for doing research with the potential to impact ordinary people. My work in this area draws tools from different fields in CS and beyond. I need to know about networking, advances in network measurements, system security, and sometimes touches of social and political science concepts. And today, I'm going to talk about the arc of projects that I'm busy with, which is first, detecting, understanding, defending against network interference. I'm going to start with the first part and go to details, and then I'm going to give an overview of the rest. Especially, I want to talk about how we can detect network interference using side channels. My work in this area appears in different papers, multiple papers, and I'm fortunate enough to work with faculties in UC Berkeley, Princeton, and University of New Mexico. For several years, researchers in the field of circumvention resistance had a long-lasting problem to solve. How can we measure internet censorship globally? What does that mean, to put it in a simple way, is how can we measure whether two hosts can talk to each other? Let's say a client in China and a server in Sweden. And we want to know that for all the clients. We want to see whether they can connect to all the servers that exist. How can we do it? Why we want to solve that? Well, first we want to bring transparency to where governments abuse their power and cause network interference. we want to tell people or citizens of the countries what they are missing and help diplomats and policymakers to come up with the right policies for the regions that the interference is happening. Prior methods to set the buffer side channels were very primitive. What researchers came up with is to put instrumentations on the client or a server. What that means is to install a software on the client and then run measurements from the client, or just pass by a Raspberry Pi, a small embedded system, to different clients around the world, and then they connect that to the Wi-Fi, and then you could run measurements from their machines. As you can imagine, these approaches are limited and have disadvantages. First, they're not scalable. How many clients you can find around the world that install your software or accept to connect the Raspberry Pi to their internet? Well, not that many. Most important, sometimes topics that you are interested to measure are sensitive, and it can cause risk to ask volunteers to run measurement from their machine for you. So there are ethical issues with direct measurement. For a variety of reasons, a client or a vantage point you have in that region can decide to stop participating in your measurement. So measurements that are collected based on this approach is not continuous. You lack vantage point very easily. Several years ago, I started thinking about this problem differently. What if, instead of putting instrumentation on client, we could measure whether the two hosts can talk to each other without being in between them, off the pass, from far away, without even having a root access or running any softwares in any participant? How can we do that? Is it the way to do it? So I pitched that in a conference to some faculties, and they said, oh God, this is challenging, don't choose that. Obviously you choose it then, and in my work in graduate school, I found a way. And this is the first thing I'm going to talk about. Look at this map. This is a map of around 140 IP addresses that speak TCP IP. What that means is, if I send a packet to any of these IPs, they follow the protocol and robotically and automatically respond back to me. Then the first question I ask is, well, how can I leverage these simple properties of the network to solve the problem I have at hand, to measure whether two hosts can talk to each other remotely, off the pass? So I came up with a technique called spooky scan. A spooky scan is a side channel, TCP/IP side channel, that help you to detect whether two remote hosts can talk to each other, and if not, in which direction the packets are being dropped. Before I talk about the spooky scan, I have to cover some background. So for any connection that is based on TCP, it needs the first TCP handshake to happen. What does that mean is you send, one party sends a SYN packet, eager to participate, send a SYN-ACK, and then you want to complete the handshake, you send the ACK. In any of the packets that go back and forth, there is an IP header. And in that IP header, there is a field called identification. For short, I call it IP ID. Remember that. I'll come back to it. And we have another part of the protocol that said, if you send a SYN-ACK to a machine that didn't send you a SYN before, you have to send a reset. There's another part of this protocol that said, if you send a SYN to a machine with open port, let's say port 80 or 443 open, that machine is going to send you a SYN-ACK. And if you don't do anything, because TCP is reliable, it's going to assume that the packet got dropped somewhere. So it's going to send a SYN-ACK for some time, like here, 3, and then give up. These are the basic properties of the protocol that I'm going to use. For a spooky scan to work, there are some basic requirements for the participant. For example, I want my client to maintain global IP ID. Remember that IP ID in the IP header that I was pointing? I want my client to assign that globally. And what that means is whenever clients create a packet and sending it out, that variable plus by 1 or incremented, no matter who is sending it. So this variable is a shared global variable. I want my server to have an open port, let's say port 80, 440, something. And I wanted to be able to retransmit signals. A machine, Roya, needs to be able to spoof packets. What that means is I need to be able to send packets using other IPs as a source IP. To be able to do that, you need to talk to your upstream and ask them to not drop your packet and let you do that. All these requirements are very easy to satisfy. They're not some magic. For example, I attended 3 universities in my career, and we could actually accomplish getting this works.
Can I ask a question on the last one there? So, I mean, the ability to spoof packets, I mean, it seems to me there's an increasing number of organizations that are trying to prevent SYN spoofing precisely to prevent denial of service attacks. I mean, if you do this at scale instead of from your one measurement machine, this is the canonical way of doing a DDoS attack, right? So, are you going to run into problems? I mean, if any hop between you and, I guess, upstream, for some definition of upstream, is doing SYN checking against the routing tables, they're going to throw your packets away.
Yeah.
How can you figure out if that's happening?
We have controls. We have the actual machine that you can actually check. Let's say you can use write backlist. We have like 10,000 machines around the world. You can check that if you're ready.
I see. So you're going to use machines that you know will respond, and you're going to spoof from those known machines to determine whether you're...
That's one way. But also I can check, like for example, the way is I will cover that, but one way is to run a spooky for a controlled domain.
Okay.
So like I have a domain that there shouldn't be...
you know there's no drops because you control all the machines. I see.
So what, you stressed global. When would it not be global? And like
the global, so it's based on operating system. Windows XP, FreeBSD, and any version before Windows XP maintain global IP. There are some Cisco versions also maintain global IP. Any operating system like after Windows XP doesn't maintain global IP. So if you look at the, I will show you how common it is. That. So how a spooky scan works, it starts by Roya sending a SYNAC packet to a client that maintains global IP ID. What's going to happen is client send me a reset. In that reset is the IP ID. So I learn the current value of the IP ID. The next step, I send a spoof C packet to the server using client IP. So what's happened is server follow the protocol and send a SYNAC back to whoever owns the IP, in that case, client. What client does is, well, SYNAC, out of the blue, reset. Consequence of sending that reset is IP ID plus by 1. Then I query again by sending another SYNAC.
So this is
and what I would see?
I missed that. So IP ID is the sequence number.
No, it's identification field that used for fragmentation reason.
Okay.
It's one field in the IP header.
Okay.
And so what I would see is IP ID jumped by 2. So roughly speaking, in the noiseless model like this, I would learn between the 2 queries IT, somebody talked to this machine.
Can I ask another question there? So you know that a packet was transmitted, right? Couldn't it also be that there's outgoing traffic from the client ID? I mean, doesn't it increment that global counter?
Noiseless. Yes, I will cover that.
Okay.
So what imagine, that would be a miracle that client doesn't
Sure.
do anything else.
Yeah.
But imagine that server to client is being blocked. In that case, the spoof SYN would get there, SYNAC will generate, retransmit it, and finally give up. But client won't see anything. So the 2 IP ID queries that I see, the delta is 1. I know nothing happened. In the other case, bear with me, it's when the client to server is being blocked. In that case, the SYNAC would get to the client. Client would generate reset. Reset won't get to the server. So server is going to retransmit, and reset is going to be created. So the delta IP ID that I would see is 4. let me give you an overview. First case, server to client being blocked. Client won't see anything, so delta 1. No direction being blocked, then I would see delta 2. In the third case, I will see delta 4. So I have 3 cases, 3 different deltas. But as you mentioned, this is when client only talk to me and the server. And this is never the case. Clients talk to so many other participants. I call all others noise. And now we have to adopt the technique to be able to work in a noisy model, noisy ecosystem. So the first intuitive way is, instead of sending 1 spoof scene, we amplify it. We send, let's say, 5. So what's going to happen is, for the first case, I would say 1 plus noise. For the second case, I would see 6 plus noise. And the third, 16 plus noise. Based on the noise of the machine, you can send or amplify the spoof scene. Also, for a variety of reasons, one of the packets can get dropped. Clients can have a burst of packets suddenly hit them. So what you want to do is repeat the measurement. So let's say I adopt a probing method as following. For 30 seconds, I'm going to do IP-ID query. I just want to see what's the noise of the machine look like. Just send 1 packet per second. And then for another 30 seconds, what I would do is sending 5 packets per sec, spoof scene, and do that for 30 seconds. So in a noiseless model, I would see this: 1, 1, 6, 1, 16. But look, and this is, I use this probing method that I talked about in real world. This is, I had a tour relay in Sweden. And these are the samples that I chose for you guys. So let's say for a client in China, tour is being blocked this way. The red line is noiseless, and the others is actual clients. For client in US, you could see that it's not being blocked. And for a client in Azerbaijan, the blocking is happening from client to server. Just by looking at the data, you can see that, well, different countries do blocking differently. But you can say that, well, Roya, 30 seconds of IP-ID and then 30 seconds of a spoof scene packet per second is a lot.
Quick question. Would this work if the sensor did not completely block the path but instead impose, say, a high packet loss rate?
So there are countermeasures that somebody who knows about my technique, for example, try to play with it. But the point is, I'm trying to measure adversaries which are like a state censorship or a government censorship. If you apply such a smart countermeasure on this national level, then it's really never happened before and not going to happen.
But do they really care whether you detect them or not?
That's another good point. Sometimes the governments don't have shame in that, that they're unplugging the internet. I mean, that's just very low in. And yeah, some countries do care about. But the thing is, what I would say is, the type of packets I'm creating is a background noise of internet. If you run a TCP dump in your machine, you will see a lot of this type of unsolicited packets come and go. So it's really hard to come up with fingerprints that is only going to pick up the spooking. If you do that, then you're going to save so much warning showing up in your IDS that you will be busy just figuring out which one is me, which one is the other.
Good question. So sometimes they just block some port, right? They didn't block the port you are using for spooky, but they might block the outer port, right?
So for the client, I don't care which port. You send the packets to either the port should be closed or filtered, closed or open. So you can randomize that. But for server, ports, for example, needs to be open. And I don't see your point now. What?
I probably say my old university, they try to block some application port for us for student, and then that's the thing you cannot detect, right?
Well, no,
We
then
can't-
I would detect that your basically firewall
Yeah.
is blocking that. That I would be able to detect,
Oh,
don't I?
okay.
So basically, the packets to that server and that port is being blocked, so I can detect that.
So we know, for example, that Iran throttles some applications and some websites. So there has been instances where they throttle protocols. So this wouldn't be able to detect that, right?
No, I mean this is black and white right now. Throttling is extremely a smart way of mimicking. What he's talking about is mimicking poor performance as a way to blocking stuff or discouraging users. And Iran used that in election 2013, a smart way. It's very hard to detect. It requires longitudinal data. Yeah. So back to the point. So a spooky scan, the first probing method that we had wasn't efficient. And one key requirements in the technique that I developed is deployment. I want to be able to run measurement globally. So I have to optimize the technique. And for optimizing these probing methods, we use the intuition from the fact that not all the clients are busy all the time. So we have different clients. Some of them are noisier than others. So for some of them, you need to send let's say 10 packets per sec for 5 seconds. For some of them, you need to do that for 30 seconds. So it depends. Based on the noise of the machine, you can optimize the techniques. So how about we adopt this probing method? For the first 5 seconds, we query IP/ID. And then for the sixth session, the 6th second, we send a 10 spoof per sec. And look at the IP/ID diff, like the delta. And do we see a jump? How much of this jump is because of my perturbation, because of my spoof scene? How confident I am? And I repeat this measurement in random times in a day to gain confidence on the detected case. The way I'm thinking is very close to what is called sequential hypothesis testing. You don't know beforehand how many samples do you need. You do collect enough samples to get to the significance that you're happy with. So as of now, this is the optimized version of the spooky. We randomly, over time of day, we do 5 and we look and try to see, gain confidence on whether we see the jump and it's because of me and so on and so forth. The detail of this is in our collect paper for those of you who are interested. So I started by saying that there are three challenges in the field to measure internet censorship globally. How Spooky can solve that? First, scalability. If you scan IPv4 on port 80 and try to find global IP/IDs, you will find around 22 million potential vantage points that I can find. There are in more than 200 countries, and the best second approach we have is it's 10,000. So you can use Right Atlas, which is another distributed network, and have 10,000 vantage points. But my technique would allow us to have potentially 22 million vantage points. So it really improves the scalability. Well, you can say that, hey, you also create some type of traffic between a client and a server. And if that client is the end user, still, that can cause risks. Let's imagine that that server that you're trying to understand whether they can talk to is sensitive. So how do you want to deal with that? Well, one thing we can do is sticking with the routers. So what we can do is just walk away from involving in IPs in our measurements. Let's say that we focus on 2 hop back from the end users. Our hope is we reduce the risk this way because it's harder for the government is knocking at the door of the router, hopefully ISPs router or organization routers, and arrest them. So it's not going to eliminate the risk, but it's going to reduce it. And how this affect the scalability, even with such a harsh constraints, I have more than 53,000 vantage points.
So a question from here, from before, what do you do with SYN dropping? I mean, users are probably not going to configure their IP tables to drop SYNs, but it would seem to me if I were running a bunch of routers on the internet, I'm going to whitelist the IPs I want to accept SYNs from, because why would anybody be connecting to my router? I mean, how many of the routers actually are going to respond to your connection events?
So look, the router is the client. So what it's received is a SYNAC and it generates a reset. And for doing that, if any port that is closed and open, if they follow the TCP,
It's supposed to do it, right? The standard says they're supposed to send the resets.
Mhm.
I'm surprised that people do.
So that's a good point. So when this 22.7 million machine that I'm talking about, they actually do.
Yeah, I mean, it seems more plausible to me that a standard TCP/IP stack on an end user machine is going to do this because it's just a Windows stack. But if I'm on a router that's a Cisco router, why has Cisco decided what legitimate packet could be showing up? I guess another way of asking the question is, so you know that 53,000 respond, so clearly some of them do. Do we have a sense of what fraction of all routers that is? I mean, is there a reason to believe that's all of them, or a good fraction of them, or do you think there's a bunch that aren't?
No. So if you look at the whole IPv4 space, there are 140 million of them that respond to TCP/IP. Out of those, there are 25% of them that maintain global IP.
Mm-hmm.
And out of those, and if you look at the routers, only 2 hop back, let's say. I would say there are more than, if I'm right, 30% of them are actually involved in my measurements. But I can give you a stats about it. Correct.
Pretty good fraction.
Yeah. But listen, the best other approach we have is going to activists and ask them for consent. And we are in a level of 100 people right now, 100, like 200, 300. So this hopefully reduces the risk and optimize the scalability at the same time. And then for continuity, well, when we were designing the framework, we hope to optimize every piece of the technique that we did. For example, for Spooky, I explained how we optimize it. And let's say this is a framework. We have this efficiency in mind. So continue as well. Also, what I have to say, routers don't work all the time, so you can keep collecting data whenever you wish. Next step was test running the Spooky scan. So we collected 2,000 clients spread over 180 countries, and we selected almost 2,000 servers that were divided in. The first thousands were results from common popular domain, and the other were from domains that were censored somewhere in the world. There is an organization that collects that. So some of them are sensitive, some of them are popular. And we keep the measurement running. So for each pair of the client and a server, we ran the Spooky for 47 times. And then after 17 days, we started looking at the data. Guess why 17 days? Paper did one. So this is, for example, an example of the results. The numbers in each of this map is the mean percentage of block server across the client in that country. And as you can see, like China stays at the top. And I have to say this. The numbers in this plot are not precise as I would like it to be, because routers geolocation suck. There is no incentives for Maxmine or any other company that does geolocation to focus on routers. So I'm working on a project to actually optimize that and make it better. This was only censorship in TCP/IP layer. As you know, it can happen in different network stack layer, such as DNS, and application layer. For the DNS, you can use the same type of mentality, which is like, hey, let's not use open resolvers around the world. Let's just focus on open resolvers that we are sure it's infrastructures or organizational resolvers. So we have a paper under submission for that. The whole idea of measuring sensitive content from an infrastructure inspired a project called Censored Planet. It's a project that UC Berkeley, Princeton jointly working on. And it's a very ambitious project. We want to collect censorship data for all the countries around the world over a long time, and so we can be able to compare these countries and provide a deeper knowledge about what's happening in each country and how differs their political events. So that was my work for the first block. I just gave a very short overview. I'm not kidding. It's a detailed overview of the first one. I'm going to give an overview of the second part. For the second part, I'm trying to understand the behavior of the intermediaries which does the interference. Especially, I'm going to focus on two systems or two studies that we did related to Chinese national firewall. These two systems that I'm about to describe are extremely interesting to me because they actively counter the traffic. In another way, I'm not just trying to detect whether interference happened, I'm trying to see how this system tampered with the traffic in an active way. Let's start by the first one. March 2015, GitHub announced that they were under distributed denial of service attack. They were receiving so much packets that they couldn't possibly respond. And it turns out the denial of service attack is because of a JavaScript that was injected into Baidu's traffic. Baidu is a search engine in China. Baidu's traffic, then the packets are going out of China. Why? Possibly that could happen. At the end, it turns out because GitHub was hosting a site, greatfire.org, and that site provides circumvention tools for Chinese citizens or talked about censorship, a status of censorship in China. So that was, at the end, we found on the target. A group of us got together to understand more how this distributed denial of service had happening. And we called the system behind this attack Great Cannon. And this is how Great Cannon works. First, if you send a packet to blah.com in China, Great Cannon will look at the traffic and let it go. Nothing would happen. But when you were trying to get to Baidu with the probability of 1/50, they would drop the actual request and then they would send an injected JavaScript back to you or the innocent browsers, innocent bystander browser. And then you would send a lot of requests to the GitHub. So imagine how many people might go to the Baidu and how many people would have a JavaScript injected in them, which lead to GitHub receiving requests. This is a very a smart way of actually creating a nation-state attack. And what we were...
Isn't the solution here that if everybody uses HTTPS, this is over?
Yeah, that's definitely exactly the point. If HTTPS was there, that wouldn't happen. What the interesting part about this was, when the researcher came to us, they were interested to know whether the JavaScript is being injected by Great Firewall of China or Chinese government or by Baidu itself. So our job was to provide evidence to attribute this attack to the Chinese national firewall. And we could only do that because we have studied China for the past decade. So we have a solid level of understanding about Great Firewall of China and how it's structured, basically we developed enough of signature for that firewall. And we showed that, first of all, this Great Cannon is co-located with where the Great Firewall of China is. So they are in the same hub. And then we showed that they are basically different systems with different goals in mind. You can read the paper for details, but at the end, we could say Great Cannon is very likely operated by Chinese government. And this is, again, I'm going to emphasize that is why understanding the behavior of intermediaries and keep tracking of them over time is important. Without such without such studies, we couldn't basically attribute this attacks to Chinese government. If you're not as scared about how Great Cannon can be dangerous to internet security as a whole, and internet freedom, obviously, imagine US defense contractor is trying to get to a server inside China, and Great Cannon has a special fingerprint for a special fingerprint for that, so they would actually realize this is initiated by a defense contractor, and they would send them an attack that hasn't been seen before. That was one of the tools that we studied. I was also interested to know how Great Firewall of China find hidden circumvention tools. Imagine that I set up a Tor relay for my friend in China, and I don't give this IP to anybody, just my friend in China. And then my friend in China connect through my relay to Tor, and therefore to the internet. How Great Firewall of China finds this IP and blocking it? This was a question I had in mind. And, well, I'm going to just give an overview of this work. So, first, all of you know about Tor. Tor is an anonymity tool that is being used widely as a circumvention tool around the world. What it does is encrypt traffic and bounce it over a series of relay that is maintained by volunteers around the world, and that way it provides anonymity and somehow circumvention. So, how Great Firewall of China find hidden circumvention tool, or specifically Tor relays. This is what it does. The first step is Great Firewalls use their deep packet inspectors to monitor the traffic. Well, if they realize that this traffic might be Tor, and how they can do that is by, first of all, TLS handshake is not encrypted, so they can look at the different fields in the TLS handshake and guess that, yeah, that's definitely look like Tor. So they guess this is Tor, but they're not 100% sure. And national firewalls cannot decide to block IP when you're not extremely sure, because it can cause collateral damage, and that can be very expensive for governments to block IP. So they have to be sure that this destination is running Tor, and not go with a guess. So what they do is a very simple act, yet very effective. They send or fire an active prober to the destination. So what they do is they speak Tor handshake to the server. And if they receive a response back, then they know that destination is running Tor. And therefore, they happily can block it. So based on these 3-4 very simple steps, they can find hidden circumvention tool, in this case Tor, relays, and block them. What I was interested was this. What's the machine behind these active probers look like? How they doing that? Like, I wanted to know how long it takes for the active probers to show up. How many active probers are out there? And so many other questions that you could ask about them. Why I do care? Because you want the next generation of circumvention tools be immune to that, and not be easily detected by this type of active probing. So like any measurement researcher, what we did is set up a test bed, measurement test bed. So we had clients inside China, and we had machines in US set up on Amazon. All these machines were running different type of Tor relays. The details, I don't want to focus on that. So, and then for each of my clients, I connect to the corresponding Tor relay every 5 minutes. And I kept this test bed running for 3 months. So for 3 months, I had like multiple vantage points inside China that were establishing a Tor handshake to my EC2 machines in the US. Then we look at the packet captures that we have to see how many active probers we observed. Well, not that many. The efforts that we put to set up that infrastructure were more than we could learn from. So as a security researcher, you start thinking like an attacker. How can I collect more active probes? Again, I've studied Great Firewalls China before, and I knew China is blocking Tor by IP ports. So your machine has around 65,000 ports, like port 80, port 1. What China does is blocking your IP and the ports that Tor is running. So how could you design a better measurement? So what I did is I forwarded 600 ports to Tor port. And from my client in China, establish a connection to each of these ports. In the eye of the Great Firewall of China, my client was establishing a connection to 600 machines. This measurement ran for 2 hours, but we learned a lot from just measurements that looked like that was based on thinking like a hacker. And also, we were lucky that one of our colleagues was running a server log for almost 5 years, so we could look at this server log and learn about active probing and when it started, what type of other protocols are being active probed. So we had all this data, and we started learning from all this, learning about the system behind active probing. The first was how many active probers did we find? Yes, in that 2 hours measurements that I did, how many active probers do you think it showed up? Just give me a number. 1,000. In that 2 hours measurement, I attracted 1,000 active probers. In the measurements that I did following a traditional approach, after 3 months, I saw 100. And in the log, we had 14,000 active probers show up. What does this teach you? That the active prober use different IPs, so you cannot look at the IP and say, oh, this is that Chinese national firewall, this is a user. So IP is meaningless, source IP. How quickly active prober shows up? So I explained the steps. National firewall, Great Firewall is using DPI, monitor the traffic, well, guess that's the Tor traffic, active probe, and then block or not block. So tell me, how many minutes or hours or less would it take for Chinese government to flag my destination as a Tor and then blocking it or detecting by running active server? It turns out in real time. So basically, the median between when my client established a connection and where the active prober showed up was 500 milliseconds. And by the way, we kept the TCP dump running by accident. And after 22 hours, we saw the active prober showed up again. Why? Guess why? So they have an IP list, IP blacklist. So every day they check the IPs. Are they still running Tor? Are they still running the circumvention Tor? And if yes, they keep the IP block. If not, they let it go.
So can I ask a question? So the implication here is that on every single TLS establishment that's outgoing across the firewall, they're then going to trigger essentially immediately a Tor probe?
No. If they look at the cipher list in the TLS handshake, and if it's look like something that they think it's a Tor, then they fire a failover. Or if it's like a
Let's see. So what is it about Tor TLS packets that look different from other TLS packets? So you're saying the cipher list? I mean, isn't that something that we can control? Or is it that we've deleted ciphers that are vulnerable? Or why are the Tor cipher? Why are Tor packets special?
Well, it is because there are a very unique number of cipher lists that the server, the Tor relays and the client can agree on. So you can actually filter on that. But for what actually?
Flaw in Tor.
No, okay. This is Tor vanilla. Actually, to fix that, Tor came up with the idea of pluggable transport. The idea behind the pluggable transport is wrap Tor traffic in another layer so that the TLS handshake is unencrypted, it's not obvious. So we have upgrades.
I see. So you do a TLS handshake that you don't trust, and then you bootstrap within that established TLS connection another TLS handshake that is now not observable that gets you onto a really secure channel.
Yeah,
Interesting.
that's one version of it. But there are so many different versions. What is it called? A scramble suit. Something you should look up. Anyway, this was just an overview of the topic, so I'm not gonna go deep. And you can look at the code and data we have and actually look at our own log to find active rollers. I'm going to summarize this by emphasizing on the fact that there are a growing number of nation-state attacks that we've seen which threaten internet security and freedom as a whole. We have a lot of middle boxes that are efficient and capable of doing many things. They're cheap as well, and therefore it can be accessible to many governments around the world, especially oppressive regime. So for us to be able to sustain current defense that we have and come up with the better ones, we need to keep track of these like intermediaries and see how they're evolved, who is developing them, and what they're capable of. That was the overview of the second part. How much time I have?
About another 10 minutes.
So I'm going to give a quick overview on a project we do for defending against interference. We had a project in mind which was how a user or an organization can avoid certain countries when they're, for example, going to a special destination. Let's say I want to go to Google.com from Iran, but I don't want my traffic to go to the US or so. And it turns out we're not alone that are interested in this problem. Brazil, after Snowden revelation, they started thinking about that. How can we make sure that our traffic that is going to Europe doesn't go to US? How can we guarantee that? So what they came up with is installing a lot of internet exchange points in the country, setting up a physical cable from Brazil to Portugal with the hope that the traffic is going to go through that pass and therefore escape US. We did an extensive study and we showed that this approach they took is not useful for two main reasons. First of all, the destination for the majority of the traffic is usually what the country is sensitive about. For example, majority of the domains, especially top domains, are hosted in US. And if you're concerned about surveillance or monitoring, well, that's a destination. You cannot avoid US. Another one was we found that even if there is a path, let's say that cable from Brazil to Portugal, internet service provider in countries don't talk to each other, and there is no coordination among them. So your traffic might not have a path to possibly go through one that is avoiding that country. In the Brazil case, majority of internet providers pure in IANA and therefore that cable is pretty much useless. What we proposed is using overlay routing. So we came up with a overlay routing system that called is RAM. And what RAM does is you go to our system and say, hey, I want to go to this domain, I want to avoid this country, give me a relay. And we have a measurement going on in the background, and we decide whether it's, first of all, you can do that, and if so, we give you a relay, different part of the world, that you can bounce your packet through that relay and avoid that concern of that. So I covered the arc of the project that I have done. The first one was targeting availability. The second one was targeting integrity. And the third one was confidentiality.